just reviewing from last year.
Yeah, you're probably doing Algebra 2 stuff at this point.
That's right.
Okay. Whenever it gets to a point where you want to switch over, just let me know.
All right. Sounds good.
The fact that you're taking an honors course, you may come across some tough stuff. That,
Yes, sir.
well, we'll get to that when we do. All right, let's get back to calculus. And we left off with implicit differentiation.
Yes.
Now, let's continue on with that, and then we'll do some real-life problems that show you why implicit differentiation is needed and so valuable. Let's start with this function. Hold on a second. Remember, I have to do this. It's the wrong one to do. I keep forgetting. I can do it, but it'll take really long to when I go to turn it off. All right, let's take a look at this. What may or may not be a function. Notice just because it has an x and a y, it could be a circle, which is definitely not a function. So, all right. May be a function, it may not. If it's not a function, it's called a relation.
Okay.
Like circles. Okay. Nonetheless, you can still find the slope of the tangent line on a non-function. And that's the point of this. Okay, so what the question is, determine the slope of the graph at that point.
All right, so
remember when you're doing implicit differentiation, which you're definitely going to do here, right? In other words, there's no way you're solving for y.
You're going to solve for it's
not
d.
You're going to differentiate both sides with respect to x. That's what you're going to do. Because you cannot solve for y. Well, and I wouldn't even say just because you can't solve for y. Even if you could solve for y, implicit differentiation would still be called for because it can be done.
Okay.
Okay. In other words, it doesn't really come down to that, but you are going to have functions where it's virtually impossible to solve for y, and this is actually one of them. However, we can still figure out what dy dx is at this point, 3, 1. So this definitely calls for implicit differentiation. So the first thing we're going to do is take the derivative of both sides with respect to x.
All right.
And that's always the first step when you're doing implicit differentiation. So let's tackle the left side first.
All right. So that is, that's just going to be, we don't look at the 3, do we?
Yeah, well, that's where we start, right there. In other words, because we're doing differentiation, you start basically assuming the power rule. And we
Oh,
may have
yeah.
to apply the chain rule and the product rule because we're going to have to differentiate the right side also. And we can see that x is multiplying times y. So let's start out applying just the power rule and then and also the chain rule. On the left side, you're going to need the power rule and the chain rule.
All right, so we're going to have 6 times x squared plus y squared. And we're going to have, that is times
what? The derivative
of x squared plus y squared. So is that going to be
the derivative of the inside? In other words, it's helpful if you think of these as when you're applying the chain rule, you're always starting with the derivative of the outside, and you're going to multiply it by the derivative of the inside.
all right? So 2x plus 2y.
Almost. Something has to follow that y because we are differentiating with respect to x. So you don't have to follow x's with anything. But when you encounter a variable that is not x, you have to account for it.
So that's times dy over dx.
Yeah, I'm going to write it like that just to save space. Okay. And that is the total derivative of the left side. Now, what's the derivative of the right side?
All right, so that is 100.
Actually, that's u right there. So if you're starting with u times v prime, then u is 100x. What's v prime?
That's y prime.
Yeah, it's 1. In other words, the derivative of the outside is 1. But since it's a y, not an x, we have to write y prime there.
Yes.
Plus, what else? In other words, that's only half of the product rule.
Oh, okay. So that would be 100 times y, or y prime.
Okay, here, hold on. Let's go back here.
So the derivative of 100x, right?
Let's see. This was, let me write this because I'm getting confused here. That's u times v prime plus u prime times v. So we got the first part, right?
Yes.
Now what's u prime?
That's 100.
And what's v?
V is y.
Yes, notice it's not y times y prime. It's just y. Because we weren't differentiating v. You understand what I'm using here when I refer to u and v?
Yes, sir.
Okay. In other words, yeah, most of these rules for calculus use u and v. They don't use x and y. So obviously that's, excuse me, that is u, that is v. No, excuse me. Yeah, I got it circled and squared already. That's u, that's v. All right. Now, at this point, I'm not going to put you through the misery of this elementary algebra. Let me just write it like this. on. I don't know how to use this program when I'm in this mode. Okay, that's going to be equal to in other words, this is all just algebra.
That's right.
This is what they're going to cover in your, there's no y primes on the right side. So the only y primes we have are that one and that one.
Okay.
So what's the next step? This is always the tricky step.
We want to get the y primes by themselves?
Yeah, factor. Just always
That's
think factoring. Since we're trying to solve, remember the original question is what is the slope? Well, the slope is always dy dx,
That's right.
which is y prime. So you end up, let me just, with this. Probably should use a different color, but my goodness. And it's never simple. It's only simple when they make up problems. In the real world, these things come out looking like this.
Mm-hmm.
Okay, so that is y prime. Can you see it all?
Yes, sir.
Okay, so what next? They want the slope at the point 3, 1.
Point slope form?
No, remember this is the slope. Y prime is the slope.
That's right.
And their question is, what is the slope when x equal 3 and y equal 1?
So you would plug in 3 and 1 into the slope.
Exactly. And you don't need to do this math. That's what you get right there.
It's just more algebra.
So that's the slope. Okay. Now,
Yes, sir.
I'm going to draw this. The only way I know how to do it at this point is this way. And figure 8, basically. That's the equation. In other words, if you go into Wolfram algebra and you put in this equation, this is what you would see. Okay?
Yes, sir.
With me? And notice that that is not a function. But that's perfectly fine. It doesn't matter. Sometimes functions are important, that we deal with functions, but not when you're talking about slope of tangent lines. In other words, our slope of the tangent line at the point 3, 1, well, what did it come out to be?
It was 13 over 9?
Yeah. That's that slope. Now, before we leave this problem, I need to rewrite it. I apologize, but remember, this is the slope. of the tangent.
Yes, sir.
Now, what's the problem here? If you're looking at this, saying that's the slope of the tangent line at any given point you want to name.
Okay.
What's the number one problem you have to consider when looking at this function? Now, this derivative function. In other words, y prime is the first derivative. It's going to give you the slope no matter what point you put in. What's the number one rule in math you can't do?
You can't divide by 0.
Okay. So this denominator can't be 0. Well, what would make that 0? How about an x of 0 and a y of 0? Right?
Okay. Yes.
So if x were equal to 0 and y were equal to 0, that's this point right here, what's the slope of the tangent line there?
It's undefined.
Because it's infinite.
Yes.
In other words, a vertical line is called undefined, but it basically is an infinite slope. And indeed, we can see that is a vertical line. Everywhere else will produce a number. In other words, if I want to know what the slope of the tangent line is right there, I can tell that it's 0. So if I wanted to solve for it, I could set y prime equal to 0, and I would find that point right there. Or that's not the only point where it's equal to 0. It's also equal to 0 right there. And that's the only 2 points where the slope of the tangent line is 0.
The origin.
Go ahead. Yeah, the origin is undefined. In other words, that's a vertical slope.
But the origin is not the only place where it can be undefined. Right?
You're right. There's also this spot.
Yes.
And there's this spot. Now the question is, if we set this equal to 0, do we find this spot? Because I think that is also a slope of the tangent line that is 0. So I suspect that if we set this to 0, we will find 3 points.
Wait, what is that? It would just
Because we have 2 slopes of the tangent line. Here, let me use a different color here. In other words, we have this slope, and we have this slope.
It would just be 0 over 0.
Yeah. Good question. If you look at this derivative function, you can tell that when x is 0 and y is 0, that the denominator is 0. Okay? It definitely tells you the slope of the tangent line is infinite. In other words, it's a vertical line.
Yes.
And horizontally, I really don't see this horizontal slope. So there's no way it can be undefined and 0 at the same time. You know, if I draw this figure 8 up here like this, that is not 0.
That's right.
So at 0, 0, we have an undefined slope. So therefore, when you take this first derivative function and set it equal to 0, you're going to solve for that point and that point only.
Yes, sir.
Now the real question is, what if you set it at a point out here? In other words, x equal to 10, y equal to 4, something like that. To be honest with you, I have no idea.
Couldn't you find two tangent lines if you did that?
No, because you're outside the domain. Or, yeah, in other words, the domain of x is not all real numbers here. The domain of x goes from there to there. So we're outside the domain. And when you're outside the domain of a function, then your first derivative does not give you the slope of the tangent line.
Oh, okay.
Okay. So you got to be a little bit careful. And let me give you another problem to illustrate that, but I don't want to leave this one yet. In other words, we can see from that there is definitely an x and a y that gives you an infinite slope, and we found that. It's right there.
That's right.
And every other point that is in the domain, I don't even know what the domain is. That would take maybe some work to figure out what the domain is, but obviously from this graph, the domain is severely restricted, so is the range. So if you ask for the slope of the tangent line outside of the domain or range, you're going to get nonsense. In the same way, the book presents a situation here. What's the slope of the tangent line at 1, 1?
Wait, is that a real graph?
It's real. No, it is not real. It's imaginary.
Yeah, that's what I thought.
In other words, this is an impossible function. You can't have this is the equation of a circle, but the radius always has to be positive. You can't have an r that is a negative number. So if you were to do this just blindly using implicit differentiation, you would come up with this. You solve for y prime and you'd get that. But that is nonsense.
That's right.
At least at this level of math. In other words, there is no slope of the tangent line of this relation. It's not even a function. If that was a positive number on the right side, it would be a circle, a relation, but it's not a function. So you got to be a little careful here. In other words, you have to be mindful of your domain and range and whether this thing is real or imaginary.
Yes, sir.
Okay. Let me do that while I'm figuring out what to go to, because this thing finally closes out, but it takes a while.
Yes, sir.
All right. Hold on, I'm sorry. You'd think I'd have this remembered by now, but what I don't understand is how come the snip and sketch, which is in the upper left, takes so long to close out? It's like my computer is backing its entire hard drive up before it closes out. There, finally.
Mm-hmm.
All right. Now what I need to do is this. Not use the snip and sketch, but the pad, and erase all the ink. Now I'm good to go. All right, let's take another relatively simple thing. Implicitly, in other words, you actually could solve for y here. What's y equal to?
Y is equal to, that's just the root at, wait,
Not root.
root x.
Not root. Inverse.
Oh, the, wait a minute, it's the, oh, the inverse sign.
By definition.
That's
In other words,
right.
if I said to you the sine of 30 degrees equals 1/2, that
The
would
inverse
be
sine of
30
1/2.
degrees equals the inverse sine of 1/2.
That's right.
Okay? So that's the way you handle these. So notice that I could proceed to differentiate the right side, the right-hand side of the page. I've got y solved for. So y prime would merely be the derivative of the inverse sine. Okay?
That's right.
Well, I happen to know what this is. It's not terribly easy to remember. I think it's that. Yeah. Okay. So I could do this explicitly. And how do you get that? You memorize it. I didn't go through this with you because I don't consider it that important to memorize the first derivatives of the inverse trig functions. I definitely believe you want to memorize the first derivatives of your trig functions. And eventually you'll memorize the inverse trig functions. It's odd. You have to use this quite a bit in calculus if you're, solving derivatives.
Yes.
Remember, you take derivatives of all kinds of functions: algebraic, exponential, trig, inverse trig, logarithmic. You can take derivatives of all of those types of functions. Okay, but let's do this one implicitly, starting with that. So when you implicitly differentiate, what's the first thing you're doing?
So we are going to try to set everything to the root of y. Is that right? Or
not really. The first step of implicit differentiation is always to differentiate both sides of the equation with respect to x.
with respect to x. Okay.
Now, this is a very, very fundamental property of algebraic equations, is you can do anything you want to one side as long as you do it to the other. I can multiply, divide, add, subtract. I can take the log of one side as long as I take the log of the other. Well, I can differentiate and integrate also. So this is the first step. I'm going to differentiate the left side with respect to x. And I'm going to do the same thing on the right side.
Okay.
So what's the derivative of the left side?
The derivative of the left side is the negative cosine.
Positive.
Positive cosine.
Derivative of sine is cosine. Cosine of what?
Cosine of y
That's the derivative of the outside.
times y prime.
Yeah. What's the derivative of the right side?
So that's just one.
Correct.
Right?
So what's y prime equal to?
Y prime is equal to
Solve that.
1 over the cosine over y.
Correct. Now, that doesn't look like the same answer, but it is.
Okay.
Okay, it's exactly the same.
Okay.
And unfortunately, trigonometric substitution is one of the hardest subjects in integral calculus. So I'm going to put that off explaining that to you.
Okay.
But just for the sake of learning implicit differentiation, then I can make that statement there, and that's actually secant of y.
Oh, okay.
So y prime, if you kind of follow the rule where you never want a trig function in your denominator, which I don't know that you can always follow that, but certainly in this case, I'm always going to give the answer like that.
Yes, sir.
Now, here, let me erase this. I got to make, let me erase pieces of it. That's the advantage of doing it this way. I'm going to draw this function. Well, this function right there is the, if you took the sine wave and draw the inverse of it, this is what you get. Notice it looks just like a sine wave.
That's right.
Okay. The only difference is this is y equal inverse sine of x. The only difference is this is not a function.
No. Yes.
And the way they make it a function is by restricting the domain. So if I'm restricting the domain here, then I get y has to be greater than or equal to minus pi over 2 and less than, greater than or less than pi over 2. In other words, that restriction restricts us from there to there. Notice that is a function.
Yes.
Passes the vertical line test.
That's right.
So usually when you talk about inverse trig functions, you have to restrict them because they're called inverse trig functions. They're not called inverse trig relations. They're called functions. And
yes, sir.
The only way you restrict that is by chopping up the sine curve. In other words, our sine curve looks like this. And if we restrict it between minus pi over 2 and pi over 2, now we're only talking about this part of it. And that's a function. And its inverse is a function. In other words, that follows not just the vertical line rule, but the horizontal line rule also, which means its inverse is also going to be a function. And notice
Yes.
all I've taken is this curve that's on the lower right, and I have reflected it across the line y equal x.
Yes, sir.
Big thing to remember. In other words, here's the line y equal x. If I take that sine curve between minus pi over 2 and pi over 2, and I reflect it over that line, I get that.
Yes, sir.
Okay. So, yeah, I guess you could actually understand the rest of this. I thought it was more complicated than it is. If I take this, remember what we got as an answer we got y prime equals 1 over cosine of y.
Yes, sir.
Well, cosine of y by the trig identity is equal to this, right?
That's right.
Cosine squared plus sine squared is equal to 1. So cosine of y is equal to 1 minus sine squared of y. So I can replace that with 1 minus sine squared of y. But remember what the original function was. Sine of y equal x. Sine of y equal x. So sine squared of y equal x squared.
Yes, sir.
So now we got cosine of y equals the square root of 1 minus x squared. Exactly the same thing we got when we did it explicitly.
Okay.
So this answer right there, y prime equals 1 over cosine y, equals this answer up there, y prime equals 1 over square root of 1 minus x squared.
Yes, sir.
Because of that trig identity. Okay. Hold on. Let me get rid of this ruler. There we go. Let's talk about second derivatives.
Okay.
Remember, second derivatives are actually pretty easy because they're just the first derivative of the first derivative. So figure out whatever the first derivative is, and then apply the first derivative to that.
Okay.
Okay, so what we're trying to find here is written like this. It's written a little bit funky, but what that means is the second derivative with regards to x.
Okay.
Okay, so the first step is always to figure out what the first derivative is. So let's go ahead and do that. In other words, we want to figure out what dy dx is.
All right, so we're going to have 2x plus 2y is equal to 0.
Hold on. We just ran into a variable that was not x.
That's right, y prime.
So there's our first derivative.
Yes.
So now, implicitly differentiate that.
All right. Now we're trying to find it with x. Okay. So would we use the division
Quotient rule.
The quotient?
Yep.
And that is.
We'll start.
It
starts with what and ends with what?
It starts with v and ends with v squared.
No, the bottom. Starts with the bottom and ends with the bottom squared. So the missing word you were looking for was bottom.
Okay. Which is v. Okay.
Okay.
So we're going to have y times just -1.
Yep, that's all. We don't need any y prime because we haven't differentiated with respect to y yet. The only thing we've done is differentiated with respect to x.
Okay.
And what's next? Is it plus or minus?
Minus.
Always. That's why the order matters in the numerator. If it was plus, we wouldn't care what the order was in the numerator. The product rule really doesn't care because it's plus. Even though
Yes,
I tell students to memorize it a certain way, you could actually do it the other way. But with the quotient rule, you can't, because subtraction is what's going on in the numerator, and you have to do that the way they give it to you. So what's the rest of it?
All right, so it's going to be minus y prime.
Hold on. Yeah, go ahead and start with the top. It'll just be easier to write. In other words, you're going to do the top times the derivative of the bottom, right?
That's right.
Okay.
So negative x times y prime.
All over.
Y squared.
And notice no differentiation going on in the bottom. You do not need to follow that with a y prime. Because all it is the bottom squared. So the way to memorize the quotient rule is you start with the bottom and you end with the bottom squared. I guarantee there's no rule on the planet that's more simple than that. Start with the bottom, end with the bottom squared.
Yes, sir.
Okay. Now, if I go further here, now that's minus y. Here, let me change colors. Minus x. What's y prime?
Y prime is that's one. That's just one.
Solved for y prime. There it is. In other words, step one was solving for the first derivative. That came out to be minus x over y.
Negative x over y.
Yeah, that's actually what we want to write in there. It's like that, as opposed to y prime. Okay.
Yes.
In other words, we've solved for y prime, so we can substitute whatever it is. All over
Y squared. Or, yeah, y squared.
Yeah. Now, if you simplify this, again, I'll save you the algebra, comes down to this. So that's the second derivative.
Okay.
Actually, hold on. Oh, yeah, we happen to know what that is. What's that?
That is 25.
Yeah, so this is really minus 25 over y cubed. That's the second derivative. In other words, when you're doing second derivatives, you don't really want your answer in terms of the first derivative, because you already know what the first derivative is right there. And sometimes you'll be able to simplify it even further. In other words, we knew that y squared plus x squared is 25. So we were able to simplify it all the way down to that.
Yes.
Now, does that have a meaning? Not at the, it's not the slope of the tangent line. It's the rate of change of the slope of the tangent line. That's what it is. The amount, it's hard to describe, but always remember that first derivative is the rate of change. So if we know what the slope of the tangent line is, which we have from the first derivative, then the second derivative must be the rate of change of that slope as we go from left to right. What's it doing? Is it increasing? Is it decreasing? So forth and so on. And what we find is it's totally a function of y.
That's yes, decreasing.
Well, it kind of depends. If y is a
Right.
negative number or a positive number.
Can you hear me?
Yeah, I can hear you. Can you hear me? Ooh, we got
Can you hear me?
I can hear you. Apparently you cannot hear me.
Something has.
Yeah, let me call you. What the heck? Garrett,
Okay, sorry about that. Sorry about that. I feel like this happens every other time.
So you can hear me now?
Yes, sir, I can.
I was about to call you. That's fine if that happens. I will always call you. And then we'll just finish the audio over our phones. But yeah, I mean, it doesn't matter what happened, but that's what I will just always do is if the audio goes out, I'll call you.
Yes, sir.
Okay, so we figured out what the second derivative was.
That's
They
right.
say, what's the second derivative when y equals 1? You know it's minus 25.
That's right.
Yeah, let's leave that thought because it's not real clear in my own mind as to what that means. Let's see, what do we got? We got a little. Let's look at real life problems. The real life problems that require implicit differentiation are related rate problems.
Okay.
Okay. Now,
Related
rate problems. Now I'm going to find one. Yeah, here's a nice simple one. If you throw a pebble into a pond, you get, here's the pebble, you get ripples.
That's right.
The radius of the outer ring is increasing at a constant rate of 1 foot per second. So what is that? That's not R. What is that?
That's
In other words, it's a changing thing. In other words, it might be the radius at a point in time, but then the radius keeps getting bigger. So what that is dr dt. That is the change of the radius with respect to time. And we know it's with respect to time because they tell us it's foot per second.
Yes, sir.
Okay, so every single second at this particular point in time, the radius is increasing by a foot per second.
That's right.
Now the question is at what rate is the total area changing when the radius is equal to 4 feet? They want to know how is the area changing with respect to time.
Okay.
Okay. So, what equation relates area and radius?
A equals pi r squared.
Now, notice what we're looking for. We're looking for a dA dt, and we're given a dr dt. The first logical step here is always to implicitly differentiate both sides of this equation.
Okay.
So what's dA dt equal to?
dA dt, that is equal to that.
It'd be 1 times dA dt, right?
Yes.
I'm going to differentiate that, and because it's not a t, it's an a, then it's going to be 1 times dA dt. Well,
Yes,
it's
sir.
the dA dt that I was trying to solve for all along. So now differentiate the right side implicitly.
So pi times dr dt squared.
Hold on, you got to differentiate the outside first of the r.
Okay, so 2r.
2 pi r,
2 pi
that's the derivative of the outside, times what?
dr dt.
Yeah, perfect. And now notice we know everything. This is what we're trying to solve for, this, but we know it's 2 pi, and they said at the moment that r was equal to 4.
Yes.
And I know what dr dt is, 1.
Yes.
1 foot per second. So the answer to how is the area changing when the radius is changing at this speed is 8 pi 8 per second. That's got to be squared. Hold on, I think. The area changes as a square. Yeah, square feet per second. Now, because if you do just the equation, you don't get square feet, you get feet. But we know, in fact, that area changes at a square foot per second.
Yes, sir.
So we always know what the units are when we're done. It's just, I'm not sure the units come out. Actually, they do, because this is 4 feet.
Yes, sir.
So if you multiply everything here together, you get 8 pi foot squared per second, which is what you're supposed to get.
That's right.
So this is called a related rate problem because you know one rate. In other words, you know how the radius is changing, and you're trying to figure out a different rate. You want to know how the area is changing when the radius, because the area is going to change differently depending on what r is. In other words, if r is 5 feet, the rate of change of the area is not 8 pi, 10 pi.
Yes, sir.
So you can only tell at a point in time or a dimension. In other words, when r is exactly 4, you can figure out what dA dt is, even though the only thing you know is dr dt. What you always have to work with is this master equation, the equation that relates a and r. And then the first step is always to implicitly differentiate that.
Yes, sir.
To get this, and then you plug in everything you know. Well, I knew that, trying to figure out that. I can do it. As long as I know everything except for one variable in the equation, I can solve for it. And we only have a few minutes here, so I'm not going to go over another more difficult one. But I am going to give you, man, there are so many, there's hundreds of examples of related rate problems that are all real life problems. You know, there's this one where you got a cop car chasing a bunch of robbers heading into an intersection. You know the cop car is going 60 miles an hour. You know its distance. The cop car has a laser gun on the robber's car, so it knows how fast they are separating from one another. In other words, first derivative is velocity. If a cop car is stationary and it puts its radar on you, it is measuring ds dt, the change in your position, which is velocity. So
Yes,
that's
sir.
how they know your velocity. They're measuring the difference in separation between you. And in this case, the question is, okay, we know this thing's going 60 miles per hour, and we know what dz dt is, because that's one of the things they tell us, because you can get that from a radar gun.
Yes, sir.
Question is, how fast is the robber car going? Well, we can figure it out. We have a right triangle right there. So the master equation is x squared plus y squared equals z squared. We can implicitly differentiate everything with respect to t, time, and we know we can solve for that at a certain point where the cop car is 6 miles from the intersection and the robber car is 8 miles from the intersection. And we happen to know what z is and what y is and what x is.
Yes, sir.
So we can end up solving for the actual speed of the robber's car without measuring it. What we're measuring with this dz dt is the separation between the cop car and the robber's car. That doesn't give you the speed of the robber's car. You have to
Yes, sir.
use implicit differentiation to do it. And this is a cool problem to understand related rates, because you know the rate of the cop car, you know the rate of their separation, you're trying to find a related rate, the speed of, in other words, dy dt. That would be the speed of the robber's car.
Yes, sir.
Excuse me, dx dt. It's horizontal. This would be dy dt would be 60, negative because it's heading down.
Yes, sir.
If the cop car was going 60 miles an hour, you know what dy dt is. You're trying to figure out the robber's car, that's dx dt.
Yes, sir.
So this is just an example of another related rate problems, and these can get complicated, super complicated. So it's probably worth our time to spend a little bit more time on this. I would say the two hardest parts of differential calculus is optimization, which we've done some of, and related rates. If you can handle optimization and related rates, you've pretty much mastered differential calculus.
Wow.
But these can get really hard. Like, here's a, I'm not going to spend much time on this. Got a 6-foot pole.
Yes, sir.
Street light right there. And you have a lifeguard running this direction who's this tall. Who puts out his shadow? You know the speed of the lifeguard, you know his height. What's the speed of his shadow? And you can see that the shadow's got to be going faster than the lifeguard, because after time, the shadow is longer, further away from the lifeguard. In other words, the further this lifeguard gets from the light, the further his shadow gets from him. Or the shadow has to be traveling faster than the lifeguard. This is a related rate problem. You know the rates, you know the geometric figure that you can set up, so you know the master equation. You can figure out what the speed of his shadow is. Some of these are cooler than everything, but this is one I always found particularly cool. In
Yes,
fact,
sir.
shadow is going faster than he is. We can do the math to figure it out. Garrison, I'm going to let you go and look forward to doing more of this next Tuesday. But if you come across some difficult stuff in your class, feel free to. I'm fine with covering that.
Yes, sir. All right. Have a good week.
You too. Bye-bye.